Hi everybody. Today I thought I'd give you an update on what I've been doing with regard to the little project on the GPS locked frequency standard we've been working on over the last few weeks. I've been working on the software and trying to make some changes to improve some of the features on this unit. One particular is to show the number of satellites being detected and also to give an indication when the frequency is locked. I've added some extra features where the display now can show the frequency in megahertz, kilohertz and hertz, so it makes it easier to read on the display. However, at the moment the frequency is still entered in hertz, and maybe that's something that we can work on later by further upgrades to the software. We'll just have a look at the new software now. It's loaded into the unit here, and I'll just go through some of the changes. When you first power the unit up, you have the intro screen, and then it defaults to the startup frequency, which is set for 1 megahertz, 1 million hertz. And at the moment the unit's probably not locked onto a satellite, so that'll be the frequency that we'll lock onto once we have a satellite lock. So I'll just take you through the buttons now. If we press the C button, it'll give you the battery voltage reading. So you've got a battery voltage check there, the same as before. Pressing D now gives you the frequency, but it's also converted the frequency in this case to megahertz. It's put the decimal point in. One change I've made on this is that when you go to frequency display, it'll display the frequency either in hertz, kilohertz or megahertz. But at the moment you still have to input the frequency in hertz. To check the satellites and whether we have a frequency lock, we now press the hash key. So I've pressed the hash key now, and what you can see there is that we now have the LCD showing us the number of satellites detected. It's showing 9 at the moment. It's now looping around in this little software loop now and checking for the satellite condition on a regular basis. That's why you see a little flicker on the number 9. And since we have a satellite lock, then it's also telling us there that the frequency is also locked. Now, to get out of the this particular mode, which is detecting satellite and frequency lock, you press and hold down the hash key button a second time until the display then changes to the current frequency. At the moment it's set at 1 megahertz. Now, to change the frequency, let's press the button A as we did before, and let me just set it at 1, 2, 3, 4 hertz, and press the B button to store that and send it into the GPS module. And this time you see now we're showing it in kilohertz, so it's showing it as 1.234 kilohertz. If we want to change the frequency again, we press the A button, we put a new frequency in, 1, 2, 3, 0, 0, 0, 0, and press the B button to send that to the GPS module. And this time, and it's again showing us now in megahertz with the decimal point in. But as I say, at the moment the way the software is working is you still have to input the frequency in hertz, but once you've done that the display will show it in either megahertz, kilohertz or hertz. If we then go back and check the battery check on pressing C, you can see we've got the battery voltage check there. Pressing D now goes back to the current frequency, which is again 1.23 megahertz. If we press the hash key again, it's now detecting the satellites, so we've got 9 satellites detected and the frequency is locked. What I'll do next is I will disconnect the antenna from the GPS module and note what happens to the display. So I've disconnected the antenna. 0 satellites, we've got no satellites at the moment, and we've got no frequency lock on there. I'll reconnect the antenna. And immediately you see we're locked into satellite. We're now receiving, we've got 10 satellites now we're detecting, and the frequency is locked again. I'll just show you the effect if I shield the antenna and just watch what happens to the number of satellites being detected. So if we put something to cover up the antenna, you can see the number of satellites is now going down. So I've got my hand over the antenna and I'm just shielding it now. We're down at 3 satellites at the moment. I take my hand away from shielding the antenna and you should see the number of satellites increase again. So we're now up at 9 satellites, and again the frequency is locked. So that's the new software running on the unit now. It seems to work quite well. At the moment I haven't used the star key. That may be something we can use at a later date for a future upgrade. One option could be to use the star key as a decimal point key if we're able to enter the frequency with a decimal point either in megahertz or kilohertz, but that's something for the future. But this particular software upgrade seems to work very well, and we now at least are able to monitor the number of satellites detected and whether the frequency on the unit is locked. Here we see the data stream that we're interested in coming from the GPS module. There are many different types of data streams used in the GPS. This particular one starts with the letters $GPGGA, and therefore we need to identify it by that start of the string. And this string of data has lots of information on here, including the current time there. You have the latitude and the longitude. The one there indicates we have a fix on the GPS fix on the satellites, and the 08 there is telling us the number of satellites that we're detecting. There's additional information on here as well, which gives information about the heights and the height above sea level, and at the end there we have a star 47, which is a checksum character to check whether the data stream was a valid one. But in our particular case today we're interested to detect the number of satellites. So in that case, on this example, it's 08, and the way we're going to do that is first of all detect this data stream, and then once we've detected the data stream we will then identify the 08 there by counting in the number of characters from the start. So the start of this data stream is 0 on the $sign, and when you get up to the 08, the 0 is position 39, so you're 39 characters down. So what we're going to do is use a substring to detect that 08 and then use that to display the number of satellites. Now before we have a look at the software that I've produced to detect the number of satellites, just a little bit of housekeeping here, because I've made a few changes to the start of the existing program. You'll recall that on the software that we currently have, we have these includes here, including a number of libraries, the liquid crystal, the keypad and the uBlocks library, which is unique to this project. And you also may remember that we've also defined the TX and RX pins on the software serial port for the GPS module, and this was mainly to do with the uBlocks library in order to program the GPS module with the configuration settings. Now you may recall that originally we had defined the TX pin here as 15, that stays the same, and the RX pin was defined originally as 14. Those two pins on the Arduino are actually analog pins. 14 is A0, 15 is A1, but from a digital perspective they're pins 14 and 15. Now as far as reprogramming the configuration of the GPS module is concerned, we only really need to use the TX pin because the transmitted signal from the Arduino is connected to the RX pin on the GPS module. So the GPS module is receiving the configuration data coming or transmitted from the Arduino. And so the fact that we only need the TX pin to be defined here, which goes to the RX pin on the GPS module, it means that we can free up what we defined previously as the RX pin, and I've changed the 14 now to 255. This is a non-existent port on the Arduino, and basically what it does, it just frees up 14, then we can use it elsewhere in our program. The software serial port for the U-Block's GPS configuration was then set here using those two pin connections. Now, the change that I've made to the software is I've included a second serial software port which I've called GPS receiver, and I've set that to 14, which we freed up from there. So 14 is now going to be used to receive the data coming from, that's the satellite data coming from the GPS module. So that is connected, pin 14 is connected to the TX pin on the GPS module. The TX pin is the one that's transmitting the data received, and then we're feeding that to the Arduino receive pin, that's 14. And again here you'll see I've used 255 for the other configuration setting, and again that's a non-existent pin because we don't need in this case to use the TX of the serial port. We only need to receive the data coming from the GPS modules. So here you can see that small changes that I've made there to the software serial port for the configuration setting by freeing up pin 14 and then using that pin 14 in the second software serial which we're going to use to receive the satellite data, and that we're now going to extract the number of satellites from. The other thing that I've included also in the start of the program is I've defined some more strings here. I've got a string which defines the number of satellites received. That's going to respond to the satellite data coming from the GPS string. And remember that in the example we showed it was a 08. It tends to have a leading 0. And for that reason I also have defined an integer, that sat number, it's the number of satellites. So when we receive the 0 in the example we showed, the 08 number of satellites, we convert it to an integer and call it sat num, and in that way we get rid of the leading zeros if there is one. I've also defined two more strings here, the GPGGA data string, and that's the data string that we're going to use for the whole data stream coming from the GPS module. And the other string there is the frequency status, and I'm going to use that string to define whether the frequency is locked or not locked. So they're the few changes that I've made at the start of the existing software. Right, well here we have the additional software that I've added, which we're going to use to identify the number of satellites and also to give us an indication when our frequency is locked. And for that I'm going to use the hash key on the keypad, so when the hash key is pressed it will carry on and do this particular sequence. And the first thing we do is we clear the LCD display and we print on the top line of the display satellites equal, and then we're going to print next to that the number of satellites that we detect. The next part of this is a do loop, so we have a do, and what this is going to do is, first of all, the GPS receiver, remember that is the software serial port that we're using to receive this data stream from the GPS module, and the first thing we're going to do is just flush that port just to remove any erroneous data that might be there. And then the next thing we're going to do is say if the GPS receiver port, if there's any information coming in on that, then we're going to read it. So this is then reading any data stream coming in on the GPS port. Now the next thing we have to do is identify the stream of data that we want to use, and remember that our stream of data we wanted starts with the letters $GPGGA, and what we're doing here is we're defining a character string which is $GPGGA, and then we're using that character string in this statement here that says look at the data coming from the serial port, and we're going to find any string that starts with those characters. And if we find a string that starts with those characters, the next statement is going to do is read that string until it sees a carriage return. So we're going to receive the whole of that string. So we've now captured the string that we're interested in, and remember that we're interested now in the number of satellites, and as I showed you a little earlier, the position of the satellites, or sorry, the number of the satellites is in the position 39 characters in on that data stream. So this is then going to look at a substring of that data string, and we're starting with character 39, and you finish at the character after the last one that you want. So in this case it's 41. So this line here is simply going to extract the data from the GPS data stream that indicates the number of satellites received. The next thing we're going to do is we're going to use the sat number integer that we defined earlier, and we're going to now convert the satellite string there to an integer by this statement here. So the sat sum equals sats dot to integer, that's going to change it to an integer, and that means that any leading zeros that happen to be on that string are now removed. And the next part of the program takes the sat number, that's the number of satellites received, which is now an integer, and we compare it, and we say if it's greater than 0, then we must know that we're receiving satellites, in which case we set the frequency status to frequency locked, and that's what we'll later print on the LCD display. If we're not receiving any satellites, then the frequency status is just a blank line, and we're printing there just 16 spaces to delete anything on that line on the LCD display. Now the next part of the program here, we have a number of serial print statements, and this is using the serial monitor on the Arduino IDE, which you'll monitor on your computer, and this is really just for test purposes. It's not used by the LCD, but I thought I'd put a few of these lines in here so you can actually test the program on your computer that it's running correctly and reading the satellite data stream. And what this will do is on the serial monitor on your computer, it will print the full GPGGA data stream. It'll then give a carriage return. It'll then print the number of satellites that we're receiving, and finally it'll print whether the frequency status is locked or not. And if it's not locked, it'll just be blank. Now the next part of this software, we're going to print the number of satellites and the frequency status on the display. So the first thing it's going to do is set the cursor position to column 13, row 0. Row 0 is the first line of the LCD display. So this is the position after we'd printed earlier the word satellite equals. And the first thing we're going to do here is just print a few spaces to clear any previous satellite number data that may have been there. So just clearing the any other numbers previously. We then set the cursor back to that position, and this time we're going to print the number of satellites that we're receiving. We're then going to move the cursor position to the second line of the LCD display, column 0, and we're now going to print the frequency status, and this will say whether the frequency is locked. If it's not locked, it'll just be a blank line. Now finally on here we have the while. This is the other part of the do loop. So what we're saying is we're doing all of this looping round and checking the data from the satellite, reading the number of satellites and the status, and then we keep looping and doing that time and time again, and it will keep doing that until we press the hash key again. And when we press the hash key again and hold it down, it interrupts this loop. It then goes to a subroutine that prints the current frequency on the LCD display and breaks out of this particular loop for the hash key and returns to the normal loop of the program. I thought we'd have a look at this unit on both the oscilloscope here and also on the spectrum analyzer over there, and just see what the performance is like. At the moment the unit is set to 1 megahertz, and you can see on the oscilloscope we have a fairly clean square wave coming out at the frequency exactly 1 megahertz. And on the spectrum analyzer there you can see I've got the centre frequency there at 1 megahertz, and we've got a nice peak there peaking at 1 megahertz, so that looks quite good actually. What I'll try and do is just shift over that fundamental frequency to the left and see when the harmonics start to come in from the right hand side. So let me just try that. I'm just shifting them across, and you should see there's the first harmonic coming in on the right there. I'll take it to the next one. There's the next one. So what we have here is we have the fundamental frequency there of 1 megahertz on the left hand side, and then the next pulse there is 3 megahertz. That's the first odd harmonic, and then the next one there is 5 megahertz. So we're getting nice clean odd harmonics when you set the frequency to 1 megahertz. So we're quite happy with that. So I think what we'll do next is we'll take it to the other extreme, and I'll key in 10 megahertz on the unit. So we now have 10 megahertz. Just look on the oscilloscope. There you can see we have some phase distortion now on the square wave, which we saw previously, but the frequency is accurate at 10 megahertz. So what I'll do now is I'll set the center frequency on the spectrum analyzer to 10 megahertz, and there you are. You can see we've got a nice clean pulse there coming up at 10 megahertz. That looks quite good. But again, what I'll do, I'll just move that off to the left and bring in some of the harmonics and just see if we can see why we're getting this phase distortion here on the waveform. So let me just shift that over. So I'm moving it across, bringing in some. There you can see some of the harmonics now coming in on the right hand side. I'll keep taking it across. That's quite strange actually, because now as I'm looking at on the extreme left there on the spectrum analyzer we have the 10 megahertz fundamental frequency, but the next large pulse there is actually at 14 megahertz. They've got another one there at 18 megahertz. There's the next one following that is 22 megahertz, and there we have 26 megahertz. That's quite strange. If I just carry on and bring another one in, the next one, so that's 30 megahertz. So that's the true odd harmonic there, 30 megahertz. But you've got these other strange harmonics here in between, and I think that's what's causing this phase distortion on the square wave here. It could well be if we have some method of filtering out these strange harmonics here, we may be able to clean up that waveform. That's something to consider for future. But nevertheless, the frequency is accurate, and if I just go back to the center frequency of 10 megahertz, you can see there we've got a nice pulse there at 10 megahertz, but then we have either side, we've got some strange harmonics which are not the normal odd harmonics that we'd normally expect. What I'll do now is I'll take the frequency down to 5 megahertz and see how that responds. So we've now got 5 megahertz there, and I'll set the center frequency on the spectrum analyzer to 5 megahertz. And again, you can see we've got a little bit of phase distortion there, but there you can see clearly we've got a center frequency of 5 megahertz, but either side of that you've got some harmonics there which are not the normal odd harmonics we'd expect. So we've got some strange, there's one at 7 megahertz there, and there's one at 9 megahertz. But the fundamental frequency there, the largest pulse there, is the one at 5 megahertz, the frequency we set it to. So let's take the setting now down into the kilohertz range. I'm going to set it now to 500 kilohertz. So I've set it to 500 kilohertz, and again now you can see that the square wave on the oscilloscope is nice and clean. And I'll set the center frequency to 500 kilohertz, and there again you can see we've got a nice pulse there, peaking there at 500 kilohertz. That's quite good. I'll just bring in the harmonics and see. We'll probably find that you've got nice odd harmonics now, but let's just bring them in from the right. Yeah, so now we appear to have got clean odd harmonics now coming in from the right there. So the pulse you can see there on the left is the fundamental frequency at 500 kilohertz, and then here you can see two odd harmonic pulses and nothing in between. So that's the reason we're getting now a clean square wave coming out on the oscilloscope. We haven't got these strange harmonics in between here that we had on the higher frequencies. Just for the heck of it, I'm just going to take the unit up to past the 10 megahertz, because it's only normally designed to go up to 10 megahertz, but I did find last time I could get up to 12 or higher. So let's just try and key in first of all 12 megahertz. Well, there we're at 12 megahertz. Strangely, we have a better square wave, a little bit of ringing on top and bottom, but less phase distortion. I'll just set the spectrum analyzer, the center frequency, to 12 megahertz, and there you can see we've got a nice clean pulse there at 12 megahertz. You can see there, you can see some harmonic there shifting in the background, and that's what's causing a little bit of the phase distortion, but we're not getting as much phase error there on this waveform than we had on the 10 megahertz waveform. And probably the reason behind that is that 12 megahertz is more of a multiple of 48 megahertz than 10 is, so that's probably why we're not getting the strange harmonics. Let me just bring in the harmonics if I can. Move the fundamental frequency to the left and bring in the. Yeah, this is looking quite nice now. You've got the 12 megahertz pulse there, and you can see the harmonics here are much lower in amplitude than what we had on the 10 megahertz, and I think that's probably the reason why we're not getting a lot of this phase distortion that we saw earlier, although we're getting a little bit of error there, but it's a little bit cleaner. Let's now step it up to 15 megahertz, see if it goes up to 15. So there we have 15 megahertz, and again we've got more phase distortion there on the waveform at 15 megahertz, and but the frequency is accurate. And if we set the center frequency on the spectrum analyzer at 15 megahertz, again we have a peak there at 15 megahertz, which is not too bad. So from a frequency reference standard, it seems to be working okay up to 15 megahertz, although the waveform is obviously not clean at that frequency. If I try to take it any higher than that, let's just try 20 megahertz. I've got a feeling this won't work, but right, now we're at 20 megahertz, and clearly we've got some problems here now. And also the frequency on the oscilloscope is showing it as 18 megahertz. So clearly, let's just set the center frequency of the spectrum analyzer to 20 megahertz. Well, the center frequency there is 20 megahertz, but you can see it's down at 18, the actual peak there. So when you take it certainly up into the higher ranges at 20 megahertz, clearly it's not working. So 15 is probably the maximum you can get out of it, but even at that, it's the shape of the waveform is not particularly clean. Well, I hope you found that update on this frequency standard project of interest. What I will do is I'll put a link down below where you can download the zip file with the latest version of the software for this project, which I've called V6 or version 6. You'll notice that when the unit starts up, the intro display on the LCD will show frequency standard V6 for that version of software, and I've done that because as we improve the software and add additional features, we can give it a different version number so you can see at a glance what version of software you have installed. But I'll keep you posted on further developments on this project. I will try and put some further information also in a link down below, which you can download in a PDF file. The thing I'm working on at the moment is a little website for Scullcom Hobby Electronics to support my YouTube channel, and what I will do is put updates on that website with regard to all the projects that I'm working on, and probably some additional information as well. The website in question is www.scullcom.uk. That's scullcom.uk, and again I'll put a link down below. Still working on that, so it's work in progress. But if you found this update of interest, please give me a thumbs up and subscribe, and I'll see you all again soon next time. Bye for now.